about linear models, right? So let's see if you still think so after the next half an hour. Okay, so linear models, like the most obvious one, linear regression. I think like all of you should be familiar with this, right? But just in case not, a very quick breakdown. So usually we have like our targets, y, right? And we have like some set, we call them features now, features inputs up to you, right? Of x, like we denote as x, 1 to m, right? And the corresponding weights. So, and this is basically like a line that we can formulate, right? Hence the name linear regression. So our output basically depends on our weighting of our features or like inputs and a bias term, right? So like this would be the offset in terms of like the y dimension here, right? So, and usually we also always assume some Gaussian noise on top of it. Well, I give it away. In this case, we assume it's Gaussian, but like some noise level. So we're uncertain about the y, right? So we have some uncertainty that like our actual target hits perfectly. And this is important because we're not sure if we have all the features that we need in order to be 100% accurate, right? So there might be something that we don't know. So we always need to account for a little bit of uncertainty, right? And not only that, but also what we'll see in a second is that like it helps us to be more robust. But yeah, let's assume that we can always usually write it down in a vectorized form, which makes the whole equation much nicer, right? So we basically don't have only have our dot product or like the scalar product between our features and our weights, right? So what does this mean visually? Well, if we have some data points on our on our x-axis, right, and we have some predictions on y, and you can see that like there's actually a lot of discrepancy, like a lot of jumps here, but we accredit this only to noise. So we basically assume that the prediction on y is slightly off for the different axes, right? So like it should be able to fit through a linear model, right? So, and then what we have is a straight line in this example, right? So it should be fairly boring and obvious, right? So just let me just increase this slightly. There we go. Straight line. And if we actually now want to do a prediction, so we look at this little yellow dot over here, right? We can project it onto our line and back on the y-axis, and this allows us to give to predict where the y value for this x would be, and we call this inference usually, right? So during inference, we basically go input and we get our output for that one. Okay, so and this is usually or like a very common approach to solve this is so-called ordinary least squares, right? Which is basically just like the mean squared error loss over here, right? So we have our target values, and then in the vectorized form, our basically like dot product. Whereas now we look at multiple xi's, so multiple data points, right? So we have for each data point we have x1 to n, right? That makes sense. And then we basically have like this, like this product will become a vector, and then we have a vector minus a vector, right? Does that make sense? All of this, beautiful, right? So again, we like to solve for beta then, or beta estimate would be what we refer to as the OLS with either right or left pseudo inverse. And so yeah, so if we actually fit it like this, and we can imagine it basically as kind of like this distance between the line and the data points, right? So that's what we're trying to minimize. So this part over here, right, refers to averaging out the distance between the point and any line, and find the line that minimizes the average distance, or the average blue lines, right? So now what is the difference here, right? Like, so on the left-hand side, we have the model interpretation, right? So what does the model actually learn, or what does the model do? And on the right-hand side, we have the algorithmic interpretations, like how do we actually get to that model, right? So what does the algorithm do in this case? And there is now like something else. So imagine we have the same scenario, well, we're like, or the same data points, but now we're not really certain about, like, so I should have visualized it here, but let's say we're not really certain about we're not certain about the exposition either. So as I mentioned here, we add noise on the y because we're not sure if this reading for the y value is actually accurate, right? But we could just as well also assume that the reading for the x is inaccurate, right? So what it means is like this could be like somewhere, let's say there's some noise here, so it could be somewhere in this area, this could be somewhere in that area, and so on. So in this case, just measuring or minimizing this distance is not really the best way to go, right? There's a much more robust approach, which would be to actually take the perpendicular distance to the points, right? To minimize that one. right? So we have the same kind of model interpretation afterwards. So it's a linear line, right? And we project our x on the line and get basically our y out. So the actual model interpretation stays the same, but we have two different algorithms now that lead there, that can lead there, right? One minimizes the distance in terms of the residual distance, right? So the wrong prediction, right? And the other minimizes the particular distance. And on the left-hand side, we have our OLS, and on the right-hand side is what we usually refer to as total least squares. So how many of you have ever seen TLS or heard about TLS? Okay, cool. Some of you, nice. Right. So, and this is basically, again, the difference between model interpretation and algorithmic interpretation here in this case. Okay, now to some questions, and this would be, okay, I don't know why it's weird here, but cool. And the question here is basically, what happens now if the system is overdetermined? Overdetermined meaning, just to be clear, like more data points than we have weights, right? So, like we're going to do a little blackboard exercise here. Where's my chalk? So who wants to tell me the answer already for the first question? Well, I'm drawing. So let's say I have like my linear system, right? And I have now, let's say, I say y equal, well, how can I do this? And let's say I have two, three, four. Okay, so we have this equation now. So what happens now if I get 10 data points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So I have 10 data points, and I only have 5 unknown. Right? So we're overdetermined. So we have more data than we have parameters. And what will happen? So this is the easy case.
We can clearly determine our weight.
Yeah, we can clearly determine our, like, we basically don't have any issues in terms of like solution space, right? There won't be an exact solution unless all of them are in one exact line, right? But since we're assuming noise in the y-axis, right, we will average it out. So like we can, without any issues, with our solution or with our approach, find one straight line, right? So there's just no exact solution, but there's usually a unique solution, right? Right? So that's good. What happens in the other case? What happens if we underdetermined? What happens now? If I give you 2 data points. Let's wait for a second. Anyone else? Like a lot of you heard about linear models, so you all should know.
Well, if it's only 2 points, we can draw a line between these 2 points and have a linear function, and that fits the data, which should be learned. No?
Can you draw only one line?
Like this?
Okay. Fine, let's do 3 then.
Okay.
Like infinite solutions for this problem.
Exactly. We have basically infinite solutions here. So that is an issue, right? So we basically can find many different ones that, I mean, they're not exactly the same distance, but the average distance will be the same, right? For those roughly, right? So we have infinite many, right? So, and why is that the case though? Let's do explainability, let's do interpretability. Why is that the case? In an intuitive way.
Because you can't fully solve the equation.
That's a mathematical way.
It's very empirical.
I would agree with you. Teaching evaluations say different, right? I had like just the other day we had an evaluation where like somebody wrote in there, what did you not like? Math. I hate math. Don't explain things in math. I was like, you're in a machine learning. I mean, what do you expect? But it's okay. No, like intuitively, look at the equation above, right? So if we have 3 parameters, right, like, or we have 3 data points, but we have like 5 unknowns, right? We can maybe fit our first 3 on the first, like, or first 3 weights on the first 3 data points, but then we're out of data points. So the other ones can cancel each other out. So I can increase beta, right, beta 4, and for the same amount, reduce beta 3, right? And so on. So this will basically, like, and this happens for all the others, like they will basically correlate very strongly with each other, which means that I don't have like a single line anymore, but I have a whole valley, right, of solutions. So if we actually look into this in a different plane, and this basically would be our, let's say, beta I, and this would be beta J, right? So we only look at 2 of those, right? We can actually say that what we end up with in an underdetermined system is not like a single line, right? But it's a whole, or actually like differently. If we would have a unique solution, it would be a point, right? But in this case, we won't have a point because those 2 can cancel each other out, right? In order to solve the equation. So we will have a line, right? And this will be a good line, and then we will have more like an area which is worse in both directions, and then even worse in both directions, and so on, right? So we have on a line now in this parameter space, we have infinite many solutions, right? Which isn't good at all. So you were laughing already. Why?
ELS?
Hmm?
ELS? Or what?
What does PLS mean?
Partially. Penalizing squared.
Okay, sure. I was thinking for a minute. So this will be one way, right? Like so, but we're gonna talk about this in a second. I thought like it was some cool acronym that young people use that I don't know anymore. So like yeah. Anyways, so does this make sense to everybody? Right? So what can we do about this? So how do we actually, like your colleague already suggested, penalizing, right? So how do we do this usually? What would be the way of doing this?
We add
Sure.
an additional loss that reduces the weights, like an L2 loss or L1.
Very good. Let's do an L2 loss. Right? So like your colleague already mentioned L2 and L1 losses. So let's say if we actually, how many colors do I have? Let's do red first. Okay. So let's do the L2 loss. Right. So we do this basically just on the parameter vectors, right? So we basically what we're trying to do is, okay, if we have infinite many, what we're trying to do is we try to find the ones that are the smallest ones, right? In terms of L2. So what would an L2 loss, right, look like now in this linear model, like or in this visualization? Second. Sure.
You would have an area around the point.
What would the area look like?
Roundish.
Exactly. So the same as we have this term here, right? Right. If we add now like the punishment term, right, on this thing, right? So we would have this roundish area, and then the size and so on that we actually, or where we actually look for an intersection, would depend on a scaling term. Lambda points, right? So something like this. So intuitively, well, so what we have here is regularization, right? So intuitively, what the L2 law gives you is basically the solution where the parameters are small enough, right, but still optimal, right? The thing is that in practice, what you usually end up with is somewhere like in this areas, right? Like some intersection around this area, which means none of those values actually 0, right? Which you might say like, okay, fine, whatever. Why does this matter, right? Because like what we're missing here is the selectivity. So we have small parameters now, but every beta will get some value, what if we have features that don't matter, right? They will still contribute to the prediction. Does it make sense? Okay, so what can we do instead? Give you a hint, the colleague already mentioned it.
Reducing the model complexity.
Yeah, well, reducing the model complexity is usually, like when people say this, they refer to basically reducing the parameter space, right? So that you have 0 parameters. But if you don't know which parameters to reduce, don't know which parameters to remove, that's exactly what we're trying to do here, data-driven, basically, right? So instead of us manually reducing the model complexity, we're trying to formulate a loss that helps us to be more selective around which parameters to use or which ones would contribute. So, like colleague already mentioned the L1 loss, right? So basically, we're doing instead, we're doing the L1 loss. So what does the L1 loss look like? For you guys, for the notation police. Any guesses? The L1 loss on the base will look like a diamond, right? And like again, same as before, determined by our lambda term, a growing diamond, right? And you can imagine now that the trade-off here, right? There's significantly the intersection point between the diamond and line will be significantly closer to the axis, right? Simply because there's all of this shape missing here between the circle and the diamond, right? And that is why we usually refer to the L1 loss as a selective loss, or as a selector, because it actually finds models where some of the parameters are 0. So it helps us to sparsify our parameter space, right? Because it basically learns 0 weighting for some of the features. Make sense? Okay, cool. So this is what we can do in terms of underdetermined systems. Of course.
Maybe I'm just confused and the question is done. But on the left side, we only have 2 dimensions, right? So we only have 2 parameters. We have the slope and the bias. So 3 points should be enough, right?
Yeah, that's I should have been clear on this. Where's my white chalk? This is y, this is x vector. So just imagine, like this is just an illustration, right? So because I don't know how to draw 4-dimensional on a blackboard, right? But it's like multiple x's, right? In fact, it's 4-dimensional, right?
That makes sense.
Okay. But yeah, sorry for that. Like always, like check me on that, right? So it's good to always clarify notation or these kind of illustrations. Yes.
In practice, do you combine L1 and L2 losses?
Interesting question. So what do we call like a regression that combines L1 and L2? Elastic nets, yes. So elastic nets actually combine those 2 losses. They're not used that much in practice anymore because they're not easily solvable in terms of analytic solutions, right? And same, yeah, for L1 and so on. Yeah, cool. So but this should give you an intuition why we even need regularization and what the benefits of L1 or L2 are. L2 has the big benefit that we basically have a very simple solution, analytic solution. By the way, what do we call it when we have an L2 loss as a regularizer? Rich regression, exactly. So L2 would be the rich regression, and L1 would be muscle. In case, I guess you knew that one too. Yes. Cool. Nice. Any questions about this before we move on? Excellent. Good crowd. So now we're gonna go a bit further, right? So like we are now experts in terms of linear systems. We know about the regularization. We know about like how to formulate them and so on. So now we actually want to look into like how we can generalize this even further, make them even more usable. Let me just quickly so this is starting. Okay, so if we have our model now, I already mentioned that for ordinary least squares, usually we assume like a Gaussian distribution for the noise injection, right? So that becomes important in a second. So if we now actually like look what that means is that we can actually reformulate this because this is what we see there it would be something basically just like the reparameterization trick, right? So by basically saying that we can like take some offset on our white noise sampled from zero mean standard variance, right? We just add something, multiply something, and that means that we can actually like create samples from another distribution, right? And this is basically meaning that like in this case, in our linear regression case, we can assume that y was sampled from this Gaussian with mean xt beta, right? And some standard variance, right? Which is the same as for our noise injection here, right? Make sense so far? Okay. So that means that if we actually look now at the expectation of that Gaussian, right? Like it's obviously again our mean, so our linear system, right? So there's like nothing new or like or important here at all, right? Well, it's important, but it's nothing like mind-baffling, right? So now we're gonna, for the sake of argument, we're gonna assume that there's now an additional function, right? That takes our expectation of our distribution and maps that onto a linear projection, right? So there is some link between the expectation of the Gaussian and that mean. So in our case, it's basically like, well, I will let you figure out what it is in OLS, but like we call this G the link function, okay? So now we understand, we can assume that our samples are drawn from some kind of distribution, right? And this is a Gaussian with the mean of the linear projection, right? And we have like some link between the expectation of this distribution and the linear projection itself, right? So this seems like a lot of unnecessary math, right? But it allows us to span a more general framework now, right? Which is the generalized linear model. So generalized linear models consist of like a linear predictor, right? Which is just a linear projection here. So we call it, in this case, I chose eta as a notation. So eta is just xt times b, right? And then we have a distribution. So usually we assume it's out of the exponential family, right? That models the distribution over y. So here, for instance, we have the Gaussian, right? And it has an expectation mu, which is just the expectation over this over our distribution, right? And as I already mentioned, we have this link function. So like the link function maps the mean to the linear predictor, and the inverse link function does the other way around, right? So like it basically goes from the linear predictor to the mean function, right? So before we go further, any questions about this redefinition or like these additional terms, right?
Would it be exponential family?
Exponential family is like the family of distribution that like basically gives distribution, Gaussians and so on, right? So there's like a whole bunch of them, right? Usually like because they kind of have an exponent in the distribution itself. Okay. So let's think about this now for our linear regression, right? So what are these terms for linear regression? So anyone wants to quickly fill me in here? Like what is happening on the left hand side? The person all the way in the back sleeping. How about you? No. Fine. Okay, so basically, like let's start with what we've already established, right? So our distribution over our y's is our Gaussians, right? And the link function is just the identity function, right? So we just basically can equate them right away. So that's easy, right? And the linear predictor is already our linear predictor, right? So there's nothing that we have to do about this at all, right? So, and this basically means that if we now look at what a line looks like when we map it, we actually can look at it now with the lens that at each point, those points are actually Gaussian distributed across the line, right? So, and this is again like something that we can interpret. We can assume here that we can look into and say like, okay, this is super interesting. So like the data around the line will always be Gaussian distributed. So if our data doesn't look like it's Gaussian distributed at different points, maybe OLS is the wrong thing to use here. Make sense? Okay. So for instance, this fellow over here, right? So this doesn't look Gaussian distributed, right? To me, at least, right? Hopefully not to you either, right? So what can we do instead? So any ideas? Let's start with the, so maybe I'll, no, okay, let's start with the exponential family. What does the distribution of these points roughly look like? Throw in terms.
uniform distribution?
Not quite. This is grown.
I think it's called Poisson.
Exactly, it's a Poisson distribution, right? So we can actually model it basically as a well, again, as a Poisson distribution, right? Which looks pretty much like this, right? So we have our mean to the power of y times the expectation of minus y divided by y fractal, right? So yeah, and this basically leads us to Poisson regression. So in addition, now we somehow, what we need to do is to map, like to establish the link function. And in this case, it's luckily just the expectation, not luckily, but intentionally just the expectation, right? So we basically get from our mean to our linear mapping just by taking the exponential, right? And that means that if we now look at the distribution, we can actually see that in terms of histograms, at least, that it follows more like a Poisson distributed way, right? So we can very quickly use now a linear model, which is still interpretable, right? By just choosing a different distribution and a different link function, right? Make sense? And we still have a linear model that is now able to model some more complex data than just Gaussian distributed. So we can even do this for this data distribution. So what would you use for this one? So it's basically, yeah, say it.
Maybe some sort of step function or
Bernoulli, right? So we can Bernoulli or binomial, right? Like in this case. So, and what we can actually say is like that it's either 0 or it's 1, right? So it's one somewhere in between. All values are either true or not true. So what this gives us the idea is that, oh, wait, we're actually talking about like just a binary like problem here, right? So we can actually say like, okay, so it's either 0 or 1, and it depends on our x-axis here. And we can use then the so-called logits as a link function. Where's my cursor? Where is my cursor? There it is. We can use then something called logits. We'll talk about this in a second, as our link function that establishes again the connection or the link, hence the name, between our mean value, right, and the linear projection or linear predictor, right? And this basically results in this type of line, right? So this is still a line, right? But in a different space, and we'll talk about this in a second. But this allows us to even use linear regression, right, or generalized model for something like classification, where we now even can say something about uncertainty, how certain we are that it's 0 or 1. Make sense? And again, we did this just by defining a different distribution and a link function, right? But the interpretability or like the line, it's still just a line, right? And this is what we usually refer to as logistic regression. So yeah, so now let's talk about the interpretation, right? So since we're talking about interpretable models, so what are the interpretable models here? And in terms of linear models and the GLM, it strongly depends on what our link function looks like, right? So for instance, in a very like boring linear model case here, right, like linear regression case, then it says that by the increase of xm by 1 unit will increase the prediction by whatever our parameters are, right? So basically, it's a direct understanding that, okay, so the weight tells me how important that feature is directly, right? Like, so changing this by 1 unit basically affects my overall prediction by beta m, right? However, if we have now something like this log link function here, then it becomes a multiplicative term, right? Changing xm by 1 unit will increase the prediction by a factor of the exponential of beta m, right? So it's not that trivial anymore. It's always by like a fixed term, right? So, but it's actual by a multiplicative term, fixed but additive term, right? But still, there is some interpretability if you allow for like a simple enough or like an understandable interpretable link function there. So the advantages here is that we're not longer restricted to this normality assumption. So we can actually model data that is non-normally distributed around our line that we're trying to match, right? We can train models that are like, as I said, that are nonlinear, right? And the disadvantage here is that the link function introduces significant additional complexity, right? So this is a little bit of an issue. And we're still restricted to this linear relationship between the parameters and the function itself, right? Data and the weights. So let's talk about logistic regression for a second. Or any questions about this so far? I think I'm a little bit slower than I wanted to be, so we're gonna speed up a little bit. Okay. So logistic regression. How many of you are familiar with logistic regression? Okay. So logistic regression is actually, other than the name suggests, a classification, right? But it's based on like using the logistic function for like or in a regression setup. So why does this work in the first place? Okay, I told you that this is a line, and in fact, this is even still a straight line. It doesn't look like a straight line, right? But it is a straight line in the right domain. So basically, what we do is we basically fit the line in a different domain that we're seeing right now here, and we project it back. It looks like that. So what does this domain actually look like? So if we would directly regress on the data, the line would look like this. So that's why we don't do it. That's a bad idea, right? So is that what logistic regression does? It's basically that we transfer our space, right, from the original data points or prediction, like into a different space where we can fit this line, right? What does that actually mean? If we visualize it, you have to leave already?
No.
Oh. Okay, have fun. Good luck. Okay, so if we look at our original space, right? So we have our x on the y-axis, and then the probability of x being 0, right? X on the x-axis, and the probability of x being 0 on the y-axis. So this looks like a space that we could potentially fit a line, right? However, the thing is that this is a restricted space, right? So there is no 1.2 probability and there is no negative probability. So our line itself, if we fit it in there, would have to be capped somehow. So that's not easy to do, right? Like at least not straightforward, right? So what can we do? The first thing we do is we introduce so-called odds. The odds are basically just the division of p of x equals 0 divided by p of x not equaling 0, right? So divided by all the other probabilities. And that actually opens up now, because the fraction, like the entire space. So we can fit a line there. So what is the problem with this space now if we want to fit a line here? Who sees it? What is the obvious thing that is like,
Right.
It's not quadratic, but what do you mean? Like, what do you mean?
Distribution between data points by the y-axis.
So you notice that the distribution is not uniform, right? So the distribution is unequal between the same values of like the same steps, right? So that is the problem. It's not quadratic, right? It's actually exponential, but like yeah. So this is a problem, right? So what we do instead then is we take the logit, right? Which is basically the log of the odds. And that allows us to bring it back into a uniform space, right? And if we have this space now, like it's unrestricted and it's like equidistant, that's the perfect space to fit a line in there. Oh, and now usually the animation should be that there is now a line in here that we can fit, right? And if we undo all of these steps, we end up with the curve, with the sigmoidal curve that we've seen before, right? So does this make sense? Why we are still just fitting a line and we just transform the space where we fit the line in, right? And that allows us to operate now on classes. Okay, excellent. So now to the interpretation of it, right? So it's like, fortunately, not as straightforward as directly for a straight line, right? But so we can basically say that like the odds change, right? So, or rather, like how do the odds actually change? And the odds change that the change of xm by a unit, right? Change the odds by a ratio of the exponential of beta m, right? So the same as we've seen before with the link function. So we actually answered this question already, right? But this is what we can see here through the derivation. And I'm not going to go through it because we're a bit short of time, but like, yeah, I mean, this derivation is also not XM relevant at all, right? It's just for you to see how we actually came to this conclusion if you want to go through it. Okay, excellent. So the advantages and disadvantages of logistic regression. It's a widely applied and well understood approach, right? Weights are somewhat interpretable, right? Again, by changing step size a little bit. It's exponential of the parameters that we add to it, right? Or like multiply by it. And we can actually have uncertainty. So we have probabilities of our classification, which is really, really cool. And the downsides are that there is no automatic feature interaction, right? So, and there is complete separation. So that's a big issue, right? How many of you have heard about complete separation? Okay, so the problem is basically what it says there, right? If one feature perfectly separates the classes, right, it would get infinite weights, and all the other features basically would be not important at all, right? And then the classification would suffer. It would actually be really, really bad for classification, right? So logistic regression makes sense if you like don't have one individual feature that is sufficient for prediction, right? Okay. So which is a fun paradox, right? Like if you have a great feature, it makes the model unusable, right? So that's kind of like fun here. So and then just like one quick thing here for all of you that might not be aware of it. Like if you have you seen or do you know what a perceptron is? Okay, basically logistic regression are the first perceptrons, right? So because it's basically like if you actually solve this, right, like you have a sigmoid here, and what it means is like you have your input, you have your activation, right, and then the activation comes out, and like your input is basically a linear combination of your inputs with some weights, which is exactly the image that you always see about perceptrons or then later neurons, right? You have like your inputs, and then you have like, so this will be like x1, x2, x3, and then you have your beta 1, beta 2, beta 3, you have your 1, beta 0, right? You have your sigmoid in here, and then you have your output. And that's what a neural network basically consists of, right? So now you get an idea. So of course, like over time, we replace the activation functions with, for instance, ReLU functions, or like other, like a more modern, like JLU or CELU, which are like regularizing. Yeah, but it's like the original perceptrons basically just follow logistic regression in that regard. Make sense? Cool. So we have linked something to something more modern. So do you feel like a 5 and 5 already? Yeah, or we're gonna finish it. So the last part of linear models that I want to talk about is generative additive models, right? So here in this case, so far, right? So we had like our like distribution that we wanted to model when we looked at our data and so on. But if you have something like this, which it's very unintuitive what the distribution might be, then of course it's an issue, right? So like just using a generalized linear model will become difficult, right? So what is the line actually that we want to fit? We can fit this line, right? We can also like try to fit something like this, right? Or something like that. So it's really like questionable what is the best line here, right? So maybe something like this works best. And the idea is that the generalized additive models try to basically take away this responsibility of just finding weights for x, right? Or like for the features that we give it, and try to abstract that with a function in itself. So we have now a feature function for each x, right? And this feature function can be different things, right? So, but in general, the idea is that we don't just have like, in this case, just a straight weighting, but we have f1, right? And if f1 basically would be beta 1 times x1, then it would be the same as the linear model, right? But it can be also other functions, right? So the idea is here that we have like the different functions. Where's my cursor? We have the different functions here and we add them up. So it's a generalized additive model, right? And f usually we refer to as the smooth functions. So in this case, what's the difference by manually adding actual these features, right? So like this would be the first question. So this just sounds like we're trying to reinvent the wheel here. But the great thing about GAM is that we don't actually have to specify the smooth function f1 like precisely. So we don't actually need to say like, oh, this is sine or this is whatever, but we can have a smooth function which is like somewhat more like able to interpolate or somewhat more able to also learn from the data itself, right? So we're going towards learned features here, right? So, and one thing we could do is, for instance, like to fit a piecewise polynomial cubic, right? Or cubic polynomial, this kind. So again, here the math isn't that relevant for the exam, but it's just like for you to like at home to explore a bit more if you wanted to. But the idea is that if we actually have now a cubic polynomial, right, and we kind of like establish our boundary conditions, right, so we end up with like a spline. And then the idea is that because the spline in itself, the smooth function, is actually just a linear combination, right, of weighted terms, right, with like boundary conditions here. I should do it this way, right? This part, right? We can break that up in our linear equation, right? So we can actually break up Fm into a bunch of different additive terms, right? What means that we are now able to, again, just learn this thing through regression. Make sense? But have like something more complex in terms of feature representation here. So, but what if we don't actually like want any particular class and so on, right? So then we actually can choose if we have something more complex, right? Or we don't like where we cannot use linear regression anymore. We're not restricted to using linear regression. Again, difference between like the model representation and the algorithmic representation, right? So we can still use the same, like learn the same model with a different algorithm. Make sense? Okay. So one way to do this would basically be through backfitting, and we're going to explain backfitting in a second now, but like for you maybe to realize, let's do step by step, right? So if we have our like smoothing functions here now in this case, and we actually just want to look at the prediction for one individual feature xk, right? So then we have like a conditional expectation, right? Which basically would look something like this, and then we can extract fk. So again, k is the index of the data point that we're interested in, or not data point, the feature that we're interested in, right? So we could write this one as fm without k plus fk, right? And then we can just pull fk out of the expectation. Make sense so far? Okay. And then we can basically rearrange this. So we want to solve for fk, right? So we basically take this conditional expectation and subtract this part, and that gives us fk, which is this line over here, right? And we can use this, or in this case, we can combine the expectations again. So because both are conditioned on xk, we can have one big expectation on it, and they're basically added together, or like subtracted in this case, right? But it's the same. So we can basically have one big conditional expectation on xk, where we take our overall prediction minus the bias and this feature here. I actually believe this should be negative too. So there's like the Paolo, can you make sure that we fix this? Like slide, just like slide 23 fixing. Okay. But again, this doesn't really matter too much. Yeah, here it's correct. Yeah. So this term here is wrong, but in here we have it corrected, right? But the idea is basically that now we can look at the individual features independently, fit all the model for the remaining features, and see now how much this feature actually like, and use basically the model learned for the remaining features to fit the current feature. Does it make sense?
Will diverge.
In what sense? The question was if it can diverge.
If one feature goes into one direction, which influences another point such that the other feature moves into the opposite direction, which then again will influence the first point, and so it could go into a kind of convergence area, but not directly convergent.
Yeah, that could happen. Like, so the idea is basically that because we do all this iterative approach instead of like batching it all at the same time, that this could lead to convergence issues and in terms of finding the unique solution or finding a solution, right? Yeah, so that could happen, and this is like one of the problems here, right? So like the tuning here is very, very like problematic or difficult, right? So yeah, so but overall, basically that's how it works, right? So like the idea here, it's important for you to understand, is that we're basically like separating our model into our different features, and we basically like learn the model and then fit the features one by one on the remaining model. And then since we iterate over this multiple times, we kind of get closer and closer to the solution. It's similar to if you've ever heard about coordinate descent. So if we do gradient descent, we do like for all the dimensions at the same time. And coordinate descent goes a little step in one dimension, then in the other, and so on. So it's very similar to that idea, right? That's how you can visualize it intuitively. And again, here the equations. But what that leads us, like allows us to do, is now to actually look at those different smoothing functions individually, right? So, and also allow for different types of functions. So for instance, we can have like step functions for some, right? Like for some of the features, which are, for instance, like more in a discrete space, like let's say the education levels, right? There's no like 0.75 of a bachelor, right? Like you have a half a bachelor's or not, right? Like you have a half a master's or not, right? This kind of thing. But we can also have like linear representations for other domains which are more continuous, or like where the interpolation makes sense, right? So these kind of things. And this allows us then also to look at those individual smoothing functions by themselves and see if we, for instance, want to maximize the salary, or see like what does the high salary actually depend on, right? Because they're like, okay, usually people in their like late 30s like are at the peak of what they earn, right? And higher educations also lead to higher salaries, right? Or like to a higher contribution towards the salaries. Yes.
Why use this iterative approach when you could do the same thing that gradient descent does in models today, which is just look at every feature at once?
Yeah, that's a good question. Like the things that like with this way, if you actually want to fit the model, like so first of all, if you wanted to use gradient descent here, you would have to formulate it all differentiable, right? So basically your parts would all have to be differential, which right now they don't have to be, right? But the other thing is also that in this case, you still kind of want to have this iterative approach because like you have these correlations, right? So the different features interact with each other. And like you basically, since you want to be more unrestricted with respect to what your features can be, again, like for instance, like step functions and so on, you can do this. But again, this is not the state of the art, right? Like this is an interpretable model. If you want to have like a more complex model where the features are also like learned and so on, like yeah, you could go in a different route, and we will talk about these analysis later on. But yeah, it's I'm sure there is also generous additive models that are trained through backpropagation, right? Or like through gradient descent, sorry. So again, this is the difference between model and algorithm, right? So yeah. So the advantages, GAM models complex, or GAMs are able to model complex relationships between features and predictions, right? The smoothing function allows also for nonlinear, non-monotonic, and like even discretized steps, right? And they actually provide valuable insights afterwards, or allow us to do this introspection on the insights with respect to the significance of the features to the overall prediction, right? At the same time, GAM interpretation can be challenging, right? Depending on the complexity of the smoothing function. So like it's not always as nice as this one. It could be also very different, right? And selecting suitable smooth functions is very challenging. Then one final step for the linear models is that the cool thing is that last year, for instance, there was a lot of like research coming out, or not a lot of research, but there's like some recent work coming out, which was very interesting as an alternative representation, right? So not like alternative hierarchical deep representation called Kolmogorov-Arnold networks as an alternative to MLPs, right? And the cool thing is if you actually look at them very closely, the math is actually very similar to GAMS. And there is even now like this connection between them and GAMS, and that actually would most likely even go in the direction that you suggested to train these as like through gradient descent, right? Okay, so with this, we're done with the linear model aspect. So it's time for 5 and 5. So again, 5 minutes. We're going to be sharp on time because we're a bit running behind. So let's go.